Previously on the OS.
And now we are only looking at this very small green part on the left side. This is the user space, and I zoomed in on this part now. Code, some data, the BSS, the heap, shared memory, shared libraries, the stacks. We are talking here about a 64-bit system, so we have 2 to the 47 bytes of memory available, 128 terabytes. So that you can randomize the locations of program sections, of libraries that are mapped into your address space, the heap, if you implement the heap, but also the stacks. If you make the addresses unpredictable, the attacker doesn't know what to write there. Let's take a look at the address space layout on Linux on 64 bits. Between that, there's the non-canonical space. We cannot use the space between those two addresses. What do we do if the memory is full? There are use cases where you might need a swap device. We throw out, we evict a page, and this is what we call swapping. Random is the most simple choice. And what do? We simply evict a random page, any page. We don't care which page, just a random page. That's the optimal PRA. Let's assume we can predict the future. The idea of not recently used PRA is basically random PRA, but with classes. And it performs better than random PRA because it takes this additional information into account. FIFO, that's another algorithm. First in, first out. In this example, better than random, but this is not generally the case. It's usually avoided for page replacement. I'm only at slide 263 out of 574. So there's still 300 slides ahead of us.
System level 101, operating systems done, far from where we started from, operating systems done.
Welcome to today's lecture. So today we are continuing with virtual memory, and this is where we stopped last time at the FIFO algorithm. Let me just arrange my windows here so that I can also see the slides. That would be great. Yes. And today we will directly continue with FIFO. You remember how FIFO works, first in, first out. And the idea of this next algorithm of second chance PRA is to make FIFO great again, because FIFO was not that great. We want to make this a very good algorithm again by improving it just a little bit. And we do that by, basically we could call it FIANRFO. So what we have here is first in and not recently used first out, and not referenced first out. So what we do here is we check the reference bit, and if the bit is already set to 1 or if it's set to 0, we do different things. So if it's at 0, then it was not referenced, so it has not been recently used, or maybe it has not been used at all, so we can just evict it. But in the other case, if R is 1, if it has been referenced, then we set it back to 0 and go to the next page. By doing that, this reference bit stores some information about whether the page has been recently used or not. And I'm just realizing that the Menti is not visible. I will, of course, make that visible here. And maybe also a bit smaller so that we can actually see everything. There's a question in the YouTube chat whether this is already the last lecture. There will probably be 2 more lecture units, where one is about scheduling and file system and maybe some other topics that we haven't covered yet. And the other lecture will be about assignment 2, but this then is labeled as assignment 2 tutorial. Okay. Well, the performance of this algorithm here might degenerate to FIFO because we are doing something very similar to FIFO. Imagine now all the pages have R equals 0, or all the pages have the reference bit set. So R equals 1 for all the pages. Then we first run through this algorithm, and then basically we have FIFO again, because it's not, it's not making a difference anymore between the pages. So what can we do? There's another algorithm which is actually used in practice, and that's the clock PRA. And it's virtually identical to second chance. The only difference here is the data structure, because in second chance we didn't really talk about the data structure. We just said, okay, it's some sort of queue, but how it's implemented doesn't really matter. In the clock PRA, this is implemented as a linked list, and we use list operations here with pushback, pop front, and yeah, if you have a, sorry, this is second chance with pushback, pop front, list and list operations. It depends a bit on the implementation here, how this actually works, but for clock, it has to be a linked list, and basically a chain of pointers, a pointer that points to the page that is the next eviction candidate. Of course, if you use a list and list operations and pushback and pop front with second chance, you can get to the same technical result. This can also be a linked list, and basically if you store where you are, the iterator, then you have essentially implemented clock under the name of second chance. The performance of this can degenerate to FIFO, and it will in some cases. So the performance might be worse than random PRA. Why is it called clock? Because the illustrations of the clock PRA illustrate this linked list like this, and basically at any point in time you have one hand of the clock pointing to the page that is going to be evicted next, and then you turn around this clock until you have found the page that you can evict. That's why it's called clock. Let's take a look at what this looks like in our PRA illustration. Let me just select the right window for that. Okay. And I also don't want to get notifications right now. That would be more convenient. So let me also close some windows here. Yes. Perfect. So, second chance or clock. Let's see how this algorithm works. We have here this array which stores for every page in RAM. For each ppn, it stores one bit of information. Has it been referenced or not? This could be in the page tables, but maybe we want to create a global data structure for these types of information. We had similar information already in the previous algorithms, so we might want to make this global, because you have to aggregate this information from the page tables anyway, across all the processes. Okay. We start again with the accesses, and basically it's random which location will be replaced next. Well, in this case, if you really talk about clock or second chance, actually, because it's so much related to first in, first out, you will always go from one side. So it's not really random what happens at the start. We start at one side and we will go through this. Okay, and then we fill the next page and the next page and the next page. And now the next, at the next step, we access memory location number 6. So memory location number 6 is this one, storing a G, and that has to be loaded into the memory somewhere. So we check where can we put it. So the pointer is right now pointing here. This is the next eviction candidate. Let's check. Oh, it's referenced. This is referenced. This is referenced. This is referenced. So we go back here. We can evict this one. Okay, so now it's exactly like first in, first out. No change so far. Okay, let's check. Okay, we have this now referenced, the others are not referenced, and the pointer is pointing here. Okay, now we get a DRAM hit. The page is already there, so this one is now referenced. The middle two are not. Now this one is replaced because reference was at 0, and we replace it. And then in the next step, we would replace this one because reference was at 0. So we always replace the next candidate that has reference set to 0. Because what happens now in the next step, the pointer is now pointing here, but it's set to 1, so we have to set it to 0, right? Oh no, actually we have a hit in the next step, so we don't really need to replace anything here. The pointer is still pointing here though. Okay, what happens in the next step? We have another hit. Okay, that's actually good. And then in the next step, yes, pointer was still pointing here. This is the next replacement that we perform. And we set this back to 0. And then we set this one back to 0, and then this one, and then this one. And then we set, we evict this one now. Which is really unfortunate because in the next step, we will use exactly that page again, but we just replaced it. So the pointer is now pointing here. And then we go for the pointer is now pointing here after the replacement. So this will be replaced next. This will be replaced next, but 5, has to replace it. Then we have another access to 4. Again, the pointer is now pointing here because after this replacement, it goes one up, and this one will be replaced next. So we have to set the reference bit back to 0 again because it's at 1. And then we go back here and go through this list again and again. And then we are here again, and now the bit is 0. So again, it acts like first in, first out, and kicks out this page here. And then at the end, this one, because it was set to 0. 3 hits, 13 misses, exactly the same as first in, first out. So in this example, it doesn't give us any advantage, but in general it might. So it's a bit better than first in, first out. So these algorithms you might already find in practice. A better algorithm that is much more relevant is least recently used. Least recently used, or variants of least recently used, is what we find in most systems today in the CPU, in the processor caches. The caches use an approximation of LRU, pseudo-LRU, and LRU uses the principle of locality more explicitly. Pages that were recently accessed are more likely to be accessed in the near future. So that means LRU will keep those pages, and pages that have not been accessed for a long time will be kicked out with a higher probability. And you might remember from last week, I recommended that you could play this game called Hanabi in your operating systems team. It's a game for, let's say, 2 to 5 players. And there you can also apply exactly these techniques and practice them in a game. Let me just check, because I think I'm going out of focus sometimes, and change that. Okay. So, principle of locality. The idea here is to evict the page that was least recently accessed. So the one that was least recently used, the oldest page, the page that, the oldest page, in a sense that pages get younger again if you access them. So we decide that this page is kicked out because no one was interested in this page. So likely no one will be interested in it in the future anymore. How do we find this page? Now this gets a bit complicated because now we need a data structure and we need this information from somewhere. So how do we do that? And the LRU data structure could be, for instance, a list, maybe a linked list of all pages. And upon access, whenever you access a page, you move this page to the end of the list. So you always know at the end of the list, there are the important pages. At the start of the list, I can kick out those pages and throw them away. So you use pop front to evict page. Can this be done in software? Good question. In software, upon every access to a page, how can we, in software, do something in the operating system upon every access to a page? If you know the answer, just write it in the YouTube chat. Let me check. There are a few people in the YouTube stream, I think. Yeah, so you should be able to give an opinion. We already have a similar mechanism somewhere, right? Where we want to figure out whether someone writes to a page. Also, while we are waiting here, that's always a good point in time to click the live button to go back into the live stream to decrease the latency. So we already use this mechanism where we detect write accesses to a page. Now we want to detect any access to a page. Page fault. Yes, page fault handling would be one option here. We'll just open also the Menti so that I also see the comments there. Page faults, of course. The problem is we would need a page fault for every single memory access. That's of course a problem, because every memory access, that means for every memory access we would have a page fault. That means we set all the pages to not present, and every time they fault we perform one small step maybe and then try to work with that. So you would set all the pages to not present except for the one that you get a page fault on. Set this one to present, then run on this page as long as you like, because that's the same page, right? But you move it to the end of the list. And then as soon as you get an access to another page, you set the previous one to not present and this one to present now. And this sounds really absurd, right? No one would use a technique like that in practice. Actually, there is a use case for this technique. If you Google SGX step, then you will find a framework which uses this to single step the processor. There's a question in Menti, let me open this right now. What is the difference between LRU and NRU? Not recently used. We will also talk about NRU in a second. Okay. I will also show the NRU algorithm on the slides. Okay. So we can do this in software, but it gives us an extreme performance penalty, and force that every memory access causes a page fault. Can this be done in hardware? In principle, yes, but there are some problems here. Reordering large data structures is not so trivial in hardware. They can have a variable size. So implementing it like this, maybe not. So this is difficult, so we get to a simpler variant of it, and that is Pseudo-LRU. Pseudo-LRU uses a global data structure to track how old a page is. And maybe a related question that you already have answered for assignment 1, where do you store the reference count for copy on write pages? You maybe already have a storage location for that. Maybe you can reuse that. Or maybe you can create another array in a similar way for these ages here. Doesn't matter if you have one or more variables of that type. When you access a page, you store the current timestamp counter, the cycle counter, timestamp counter, in this array. That means that you now know when the page was last accessed. When you replace a page, you can simply search this data structure for the lowest stored value. This is now more expensive than just taking the first element from the list, but it's possible without reordering the data structure. This is a pseudo-LRU variant that we can implement. Okay. Yeah, can we implement this? I already answered it. We can implement this. There's no expensive reordering here. The problem that we still have is upon access to a page. So this is still difficult. We need to approximate this. But we saw a trick in the last lecture. We used a trick to do that upon access to a page, to do something there. There's a question in the chat, why do you need to remove the lecture after the end of the semester? Let it be there for all to learn. In principle, I don't have to remove it. The problem is that I'm still a bit of a burnt child from lecture recordings that we did like 10 years ago. And there we had the problem that in one semester we put all the lecture recordings online and kept them online. And then in the next year, the number of students that were in the lecture hall dropped drastically to, let's say, 20 to 30 students. And at the same time, the grades dropped also drastically. We had only very few ones in that semester. And then we said, well, the only difference that we changed was that we provided the recordings, and therefore students assumed that just watching the recordings gives them the same experience and the same learning experience and the same learning success as being in a lecture live and being able to interact with the teacher, being able to ask questions whenever they pop up. And also it's a matter of when you watch a thing that happens live, you watch it in a different way than something that has been pre-recorded. And my impression is that people are more attentive in the case if it's live. Let's talk about Pseudo-LRU. Pseudo-LRU, we just said we need this trick how to get the time, and we use the same trick that we saw in the last lecture for the other algorithms. So we will pull the page tables and read these reference bits and reset them, and now we know, basically every time we read them, we know, now it has been accessed, or if it was 0, then it has not been accessed. So from that we know, at least we can basically sample when the page has been accessed or not. We're basically just sampling these page tables at a certain frequency. Then we store the current time value in this global data structure. And I'm saying global here because it probably should be global across the entire kernel, and also in terms of a variable. Probably you will use a global variable here. Global variables are really good and you should use them. There's no reason to be afraid of global variables. When do we do this? Yeah, that's a bit tricky. When do we pull the page tables? There are different options what we can do. We could, for instance, run a thread, a page replacement thread or a swapping thread. But in this case, probably a page replacement thread. And this thread could continuously run and check through all the pages from all processes and basically read those reference bits and reset them and store them in this global data structure, the RDTSC value then. Would be one option. Another option is whenever you deschedule a thread, and this is maybe a bit more clever, because if you run a thread, how would the thread know what to check? But upon descheduling, the thread that was just descheduled only needs to check through its own page directory. And you can check the reference bits on any level. So on the page map level 4, you can check already which entries were referenced. One level down, which entries were referenced, And you can always check those bits and you will know whether the page has been referenced or not. Okay. This gives us basically the LRU PRA, which is more like pseudo-LRU, but it's an approximation of least recently used. The performance of this in general is quite good. That's why it's widely used in practice. You will also find a different approximation in modern CPU caches that just works with a finite number of elements, but then just swapping elements, and by doing that, organizing them in a tree and knowing which element is the oldest one. The performance can, however, also go down quite a bit if you, for instance, have, let's say, 8 megabytes of RAM and you loop over an array of 8.1 megabytes, then that's super bad, because all the time when you run through these 8 megabytes, you always evict what you would need next. So you always have this 0.1 megabytes that you can't just fit in. And that means that the oldest page is at the same time, the least referenced one, is in this example the one that you will need next. And that's pretty bad. Let's take a look at the performance of LRU in exactly the same example as before. In the beginning, we don't know what's in the RAM, and also we don't know when it was last used. So we assume that we just fill it up from the bottom, and we start here. This was used in time step 1. So I'm taking the time step here as the value for RDTSC, but you could use any time value basically. What I wouldn't recommend is using something that is so coarse-grained that there is no difference anymore between different threads. So something like the scheduler ticks might be a bit too coarse-grained. Okay, so we set timestamp 1 here, timestamp 2, timestamp 3. This one is the eviction candidate now, and it's evicted. And now we can see that this one is the least recently used one. The entry number, what is it? Entry number 5 contains an F, and it has been used at offset, timestamp offset 1. So we kick out this one next. So if we access this location, this will go here. Now this has been used in timestamp 5. Now this is the next eviction candidate because it has the lowest number. It has been least recently used. Then the next access goes to number 7. Okay, this one, it's a hit. Okay, next step is access to 3. That should be 0, 1, 2, 3, this one. And that means this one will go here because this one is the least recently used one. And here you can already see that the algorithm behaves now a bit different than, for instance, clock that we've just seen before. Okay. In the next step, this one will be evicted by the access to offset 1, offset 1. And then in the next step, we have another hit. That's great. This is now very recently used. That's offset 9. And this one is now the least recently used one. Okay, let's see what happens in the next step. We access offset number 6. This is a hit. Okay, very good. Then in the next step, we access offset number 2. And as you have seen, this one was the least recently used one, so it's evicted. In the next step, we access offset number 7. It will be a hit. In the next step, we access offset number 0, so it has to replace this one. In the next step, we access offset number 5. And number 5 is 0, 1, 2, 3, 4, 5, this one. And it will go here. So it replaces G. Data G is replaced by data F here. And then we can see that this one is the least recently used one, the number 11, and 11 will be the data here is, let's see, from address number 2, and it will be replaced by E from address number 4. Okay, and in the last step, H will be replaced because it's the least recently used one now, and it will be replaced by offset number 3, 0, 1, 2, 3. This one will be placed here in the DRAM. That's actually quite good. 4 hits, 12 misses. That's actually quite good, better than before, right? So this is a quite nice algorithm, and this is also used in practice. So there was a question before in Menti, and the question was, I will just check this out again. What is the difference? I will just show this again, this question. What is the difference between LRU and NRU? LRU, I'm already on the next slide, so let me just hide this one for a second. LRU is about the least recently used element, and this one is kicked out, as you've just seen. Not recently used was an algorithm that we saw last week, where we just kick out pages that have not been recently used, so we always reset these bits and kick out those that have not been recently used. But not recently used does not take into account any time or anything, so it's much less precise and uses the principle of locality to a smaller degree. So least recently used uses this to a higher degree. I hope this answers the question. If not, feel free to ask again. But now that we also saw least recently used, we can also talk about the differences here. Okay, so let's continue with the next algorithm, not frequently used. Also an algorithm that you might want to know. Again, it uses the principle of locality, and it has a bit of a different idea here. And the idea is not to use when the page was last accessed, so not the time since this happened, but the frequency. The frequency of accesses should decide which page is evicted, and the one with the lowest access frequency is evicted. If you want to go back here to this principle of locality, let's maybe quickly recap this. We had this example with the tires, and where the tire exploded, let's say one day after I hit a sidewalk with a side curb with a tire of the car. And what you can conclude then is that probably there was a causal relation between those two events. If they are 1 year apart, probably there was no causal relation between those two events. With not frequently used, you're not looking at the distance since this happened, but you take a look at how often this happened. So let's say, for instance, you drive every day across a very rough road with a lot of small stones, and then one day you have a flat tire, and you drive over this road every day. And one time in this year, you drive, you touch a side curb or a sidewalk with the tire. You drive up this corner, and the wheel doesn't like this, the tire doesn't like this. And now one day you have a flat tire. What's the more likely explanation? The 365 times going over this stony road, or the one time where you hit the sidewalk? And then let's turn this around. Let's assume every day you hit a sidewalk for some reason, and one day you drive across a stony road, and at the end of the year you have a flat tire. What's the more likely explanation? What is the causal relation here? And following this reasoning, the principle of locality also makes sense here. The frequency can also be a meaningful metric to decide which page should be kicked out, not just the time since it happened. So we can approximate the frequency by using the access count. So how do we do that? How do we get the access count? we have again a global data structure. I like global data structures for the frequency of each, the access frequency of each physical page. When we access a page, we need to increment this access counter. Instead of just putting a timestamp there, we now count up. And for the page replacement, we now use again a search, and we search for the lowest counter value, not for the lowest timestamp, but for the lowest counter value. So we might even be able to reuse the search function here that we've implemented for LRU anyway. Okay. Can we implement this? Of course. Same trick as before. We poll the page table, we read and reset the reference bits, we increment the access counter. And when do we do this? Again, we can decide when we want to do this. Maybe a thread does this continuously, runs and checks all the page tables of every process. Or maybe upon descheduling, we can also transfer this data into this global data structure, this information. And this gives us the not frequently used algorithm. Okay. What is the performance of the not frequently used algorithm? Let's take a look. It can be nice. It can be nice for some examples. It can be good, but sometimes it's not very good. And for some pages especially, it's not very good. For instance, boot code. Boot code is very unlikely to be swapped because it was accessed a lot of times during boot up, and we just approximate this access frequency with the access count. So this code will always stay very important. Let's take a look at this example here with our time series with the accesses. And we will again start as in the last examples. And now we have an access to each of these pages, one access each. So which one is evicted? Well, now they have all the same access counter. And we want to access this page here. So where does it go? I don't know. Let's throw a dice. Let's use random again as a fallback. Let's pick this one. Okay, so we put it here. And in the next step, we access page number 7. Okay, sounds good. Now this is at access counter number 2. Maybe you already see a problem of this algorithm. Let's access the next page before you all see the problem of this algorithm. Offset 3 is this page, and we are putting it in one of these 3 here. Which one do we choose? Let's maybe pick this one. Random, right? And the next access, offset number 1. Maybe offset number 1, it's random. Maybe it goes to this location here. Sure, why not? And then we have an access to number 7 again. And it's already in the RAM, so it's now at access counter access counter 3. So this is really nice. This page is never going to be evicted, right? Okay, let's see what happens next. We access page number 6. Now this page is at offset at access counter 2. So this page now also has a lower probability of being evicted. Actually, it cannot be evicted right now as long as there are pages with access counter 1 around. Okay, let's take a look at the next access to offset number 2. It has to replace one of these 2 here because the others can't be replaced anymore. Okay, this one maybe. Access to number 7 again. Great. So this is nice. So this is at access counter access counter 4 now, and that means it's never going to be evicted anymore. Access to number 0. This is nice. We access this one. It's a hit. And now you see probably what the problem is of this algorithm. Take a look at the array here, 4, 2, 2, 1. Can we ever get out of this situation again? What happens in the next step? We access offset number 5. That's this F here. Where do we put it? Of course, here. This is the one to be evicted. And in the next step, access to number 4. Great, number 4, that's this one. Where does it go? Here, because this is the one to be evicted. Access to number 3. Of course, this one. Where does it go? Here. Oh, Oh, this is really bad, actually. And let's take a look at the numbers. This actually had 5 hits and 11 misses. So it looks as if this algorithm was really good. But you can clearly see that it's not good, right? So hits and misses with this small example might not even be the best metric here. We might need a lot larger access streams. So we would need real-world benchmarks to actually assess based on hits and misses whether one or another algorithm is better. And it might change for different systems depending on how much RAM you have. Different algorithms might perform differently, and the workload that you have. So if you have a workload that requires a lot more memory than you have, or if you have a workload that requires just a bit more memory than you have. So different algorithms for different purposes here. And this one, you can clearly see that it will get worse and worse over time because it will only put pages here. And if there's no access ever again to any of these 3 pages, then it's just bad for us because it's as if we would only have this much of RAM, only 1 slot instead of 4. So there's a problem. This algorithm has a big problem, right? How can we fix that? Or let me ask it differently. What does this algorithm need to do to not suffer from this problem? Reset after a certain amount of time. Yeah, resetting is a bit drastic. Maybe we can find something that is less drastic. Decrease it over time. Yes, and this is what gets us to aging. The human brain, or in generally any brain of any living being, needs to forget. Forgetting is an essential property. You need to make things that are not important for you right now, you need to be able to forget them. If you are not able to forget these things, to put them further back in your mind and not be able to think of them ad hoc anymore, then this will cause you problems. This is well studied, and this is a problem that is known from psychology and from neurosciences. We can use the same techniques here that allow us to handle a lot more information over time by being able to forget things, and we can let the algorithm also forget things. And I'm not speaking here about a very drastic periodical reset, right? I mean, some humans also do that, the periodic reset, but I'm not talking about that. So we are talking here about just forgetting it a bit, as we humans do all the time. So NFU has this problem, it does not forget. Maybe we should make NFU's memories slowly fade away, as real memories also do. And that means we let the access information age over time. Okay, how do we do that? How do we let it age over time? And still, same question as before, how do we observe an access to a page? We use the same trick as before. We use a global data structure for the age, and upon access, we set the most significant bit to 1. So you can see that this is actually a value of 4096, but I store this in binary here. I print this in binary, as you then can immediately see what I'm doing with aging here. In a constant frequency now, because age progresses at a constant frequency, all pages, the age of all pages is shifted by 1 step in this global data structure to the right. So you can see that this, for instance, happens for our value from just before. We shifted 1 to the right, and now it has become 4096 has become, oh, what is this? This is 4 and 8. So this is 2 to the 8. It's 256, I think. Might be 256, yeah. So we decrease this by quite a lot by shifting this to the right. Actually, sorry, I was wrong before. This is of course not 4096 because it's not hex, it's binary. So this is actually 2 to the 3, 4. Yeah, we have here 2 to the 0, 1, 2, 3, 2 to the 3. So this is 8. And then we have here 8 and we shift it to the right and then it becomes 4, of course, because it doesn't make any sense to store this in hex. It would have the same effect, but we would have just multiplied all the numbers by, we would have blown up all the things and would have needed more memory. With a binary number, it's of course a lot more efficient, even if the same thing happens. For the page replacement, you search for the lowest numerical value, and that means the highest age, or the page that has been aged the most time. Let's imagine this happens not just once but more often, then the value will at the end be 0 even. And then you can easily say, okay, it's 0, so this is one of the oldest pages. Okay. Can we implement this? Of course, we use the same tricks as before. We poll the page tables, we read and reset the reference bit, we set the most significant bit in the global data structure. And when do we do this? Before aging, either that, when we shift this, and this has to happen on a regular frequency, or upon descheduling again, transferring these bits into this global data structure. And then the regular part only is the aging. When do we do this aging, the shifting of the values? It's not really helpful here to use a thread for that, because this should happen on a regular frequency and threads are not scheduled on a regular frequency. So we set up a periodic time interrupt. Actually, we already have timer interrupts, right? We can maybe use that. Upon every nth timer interrupt would be one idea how to do that. We can also set up a special interrupt for that, but the time interrupt is also fine. And that gives us the aging page replacement algorithm. What about the performance? The performance of this is generally considered very good, because you get the advantages from the not frequently used algorithm, but without the disadvantages that it introduced. So it's again taking the principle of locality a bit more into account, because it forgets information, principle of locality. One of the most widely used PRAs in practice, yes, aging is widely used. You will also find, however, that variations of clock are used in practice, and sometimes it's difficult to tell what the actual algorithm now actually is, because it has evolved over time. So in Linux or Windows, you will find that there are way more sophisticated algorithms that have been optimized over decades by now to tweak out the last bit of performance and to smooth out all the edges that we have in these corner case situations. Let's take a look at aging PRA again in our simulation. So we have our access stream here, and we can see the ages here. I illustrate this now with 5 bits, I think. 5 bits, is it 6 bits? 5 bits. 1, 2, 3, 4, 5, 6 bits. Okay, 6 bits. And we can just start at the bottom again, place the memory memory content here in RAM, and update the ages accordingly. And you have seen what happens here. We'll go through this again. We start here, we put this here, so now this is the age. It's very young. This is now same age. And now after 2 memory accesses, maybe we already have the periodic timer interrupt that ages the pages. So in my example, it's always after 2 steps you will have the periodic timer interrupt. You can see this here, periodic timer interrupt. and now it has been shifted by 1, so it's a bit older. But now you can see this in bold here. This is the oldest page. So this is evicted. Now these two are the oldest pages. One of them will be evicted. Now this is the oldest page. This will be evicted. But we get a cache hit first, or DRAM hit first in this example, because it accesses a location that is already there. In the next step, we access location number 3, then this is replaced. In the next step, we access location number 1, so this one is replaced because it's the oldest age. And you can again see from this step to this step, there was again some aging. So the red page is now a bit older, the blue page is a bit older, the orange page is a bit older. This one is at the youngest age because it has just been accessed. What you can also notice here, look at these bits here, 0, 0, 1, 0, 0, 0. And as soon as we replace it with new content, then this information does not belong to this new page. So we have to overwrite it as soon as we load a new page into memory. See, we did this. There's only one bit set, not the other bit that would be set if we would keep this information and just OR the one to the top. And we replace always the page that has the oldest age, the highest age, and that means the lowest numerical value in this example. This one has the lowest numerical example, and in the next step we shift again. So here we access offset number 7 and we shift. Okay, you can see that it was shifted. It's still the oldest page. Then we have a hit on this location, so it's now the youngest page, and these two are now the oldest pages, and one of them is going to be replaced in the next step. Let's say this one. So this is replaced. In the next step we have an access to number 7, so it's again a DRAM hit. Then we access location number 0, it will be placed here. Then we will access location number 5, it will go here, replace this older page here. And then we have an access to number 4, which will go to this location here. And at the end, an access to number 3, and it will go here. 4 hits, 12 misses, so it performs similar to the other algorithms on this small example, but it's used widely in practice as the performance is quite nice over larger numbers. Okay. There's a question in the chat, and it says, will we need to implement any eviction policy in A2? Actually, you are expected to implement multiple of these and compare them and see which one performs best in your SWEP. So you would probably at least implement something like 2 or 3 or 4 PRAs and then compare them. There are some limitations of aging, of course. For instance, if you, as you've seen, some pages sometimes have the same age because they were accessed in the same cycle, basically. Also, you will have a limited number of bits. And yeah, the limited number of bits can be a problem. If the counter is 0, then there is no difference whether the page was unused since 10 or 100 ticks. So there's not really a difference anymore, and you don't have this information anymore. So compared to LRU, in this case, it might perform worse than other algorithms. More bits can be better, but the question is how many, because if you use 64 bits, then probably the last few bits will rarely matter. So you have to find a good trade-off here, how many bits you want to use. And you can try that out. You can implement aging, try it out with 8 bits, with 16 bits, with 32 bits, and check out for one test case for swapping whether it performs better with fewer or more bits. Okay. With that, we get to a question in Menti. Let's see. Which statement is true, it says here. So I prepared some statements and I want to know which of these is true. And you can find the Menti link down here in the description. You can directly click it or enter this code on menti.com and you will be able to answer the question there. And I will wait a few more seconds because we have 30 people now in the Menti. That's approximately half of the people that are watching. Again, if you are not live, I keep saying this, but if you are not live, click the live button during the quiz. There's nothing you can miss because you will get the prompt on your device anyway, and that means also keep an eye on your device so that you can see whether the prompt already starts and the question is already there. 40, 45 now. I really don't know why this number sometimes drops, so this is a bit weird, but let's assume we are complete now, and let's just start the quiz. So keep an eye on your device. I'm starting the question now. Okay. Which statement is true? LRU is worse than FIFO. NFU is better than LRU. Aging is better than NFU because it forgets. And we can see that most of you have already answered. There's still 10 seconds left, but as you see it in the stream, and me saying this in a stream, there's probably almost no time left, because that's approximately the delay we have, even if we click the live button. And the quiz is over, and most of you have listened today and understood that aging is better than NFU because it forgets. The other two are not generally true. LRU is usually not worse than FIFO, and NFU is usually not better than LRU. Okay, let's continue. Maybe we can improve something more, because we used the principle of locality so far with respect to time and something happens, but maybe there's also another thing that we can take into account here. For instance, let's assume I drive with my car over a sidewalk with a tire, and it sounds really awful, and probably the tire doesn't like it. And the next day, the tire of your car explodes. Is there a causal relation? Probably not, right? Because it's your car, it's not mine, right? So we don't take this other part of locality into account, where it's about my resources, your resources, and also about fairness. So far, we completely ignored processes, and we could use this information to get even better at swapping pages. Process-aware page replacement algorithms. Can we make PRAs more fair? The question is, how do we make them fair, right? What means fair in this context even? Process performance. How do you compare the performance of GTA 5 to a calculator? Whose performance is better now? And you want to have them run at the same performance, so how would that work? Or maybe sometimes you want to maybe fairness. You could measure this as the same amount of memory for every process. Let's imagine again, Tiny Shell versus 3D game, or a calculator versus GTA 5. Are you fine if GTA 5 gets the same amount of memory as your calculator app? Probably not, right? So you want to find a proper way to measure fairness. And the thing that we want to focus on here, as we're talking about page replacement, the thing that slows these processes down are page faults. And this is sort of like the kind of democratic fairness here, right? It doesn't mean that everyone gets what they want, but it just means that everyone is equally unhappy with the outcome. And that's also what we have here. The same page faults per second, so the same page fault frequency for every process. All the processes are equally unhappy. They are equally slowed down with the same page fault frequency. The calculator app, if it doesn't use a lot of memory, well, it should still be slowed down as much as GTA 5. So if GTA 5 is slowed down, calculator should also give away pages and be slowed down. How do we make sure that every process has the same number of page faults per second? With the page replacement algorithm. There's a question, but what if my calculator needs to do some very heavy calculations? In that case, you might want to prioritize processes. You want to introduce process priorities, and they could take into account that the page fault frequency for this process should be lower than for the others. Let's talk about another problem before we go into these process-aware algorithms. Thrashing. Thrashing is if a system deals if it spends more time on handling page faults and swapping than with actual work. So this is pretty bad. You don't want the system to work on page faults and swapping most of the time. Most of the time it should do the work. So this is pretty bad. And if processes need more RAM than there is, then you will always have too many page faults. And that means, I'm just wondering about I can see it now. So this is a lot of pages. So we need more RAM than exists. Then we will always have too many page faults. If the page fault frequency is too high, what do we do then? Buy more RAM, right? Of course. Or a solution could be for the operating system to swap out an entire process, because there is not enough memory for all the processes to run at the same time. The system starts thrashing. So what we do instead is we put certain processes asleep, put them to sleep, and then we will instead kick out all their pages. And the page fault frequency should decrease then because we have more memory available. And then we schedule it later as soon as we have more memory available again, because some other process is terminated. So another approach here would be to only schedule processes where all required pages are in RAM. And this is basically the start of the working set definition. Working set definition goes back to the 60s, and there the definition by Denning was we define the working set WT tau as a process of a process at time t to be the collection of information referenced by the process during the process time interval t minus tau until t. So basically it says the amount of memory that I accessed in the last tau interval. And tau might be something like, let's say, 5 seconds. So any page that was accessed in the last 5 seconds. Tau is the working set parameter here, where you can tune how large the working set is. Then we also have a function omega t tau. That's the number of pages in this working set, not the actual pages, but just the number of pages. And a lot of ideas were derived from this working set idea. Most of these ideas were focused on pre-paging, so you would preload all the pages that are in the working set before scheduling. In case of a PRA, you would only swap pages that are in no working set. If the page is in no working set, it can be kicked out. And for that, you need an adaptive tau, because you don't want to keep tau at the same level. If you get more and more processes that consume more and more memory, you have to reduce tau to be able to kick out a page. So if you take a look at this function over the size of tau, you will see that the working set size will increase very quickly, but then at some point not so much anymore. Because again, principle of locality, the process will very likely work on some set of pages, and this set of pages will not grow linearly, but after some time it settles due to the principle of locality. So what we can do here is we can define the working set size via the time. So that means all pages younger than tau are in the working set, as suggested by Denning. But this can be a bit difficult, and there are alternatives. For instance, you could use a huge shift register. Shift in page numbers upon access, and then you basically also store the n youngest pages, right? You can just say, okay, everything that is in this shift register has a size of, let's say, 128. These 128 pages are in the working set, and you just push back, pop front, and then other pages are in the working set. Would be one way to implement a working set algorithm. Or you can work with the page count. Every process would have an n, so you can also see this here. Tau is, of course, process specific. This shift register, the size would be process specific, different for every process. GTA5 needs a larger shift register than your calculator because GTA5 will use more pages. The page count, the n would be a process specific parameter, and it means the n youngest pages are in the working set. So you need to store which pages are the youngest one, and then you just count 1, 2, 3, 4, 5, 6 up to n, and those are the pages that are in the working set. If the page fault frequency is too high, what do we do then? We globally reduce tau, or the size of the shift register, or n. Okay. Pre-paging today is, I would say, not that common. Actually, we have other algorithms that do something similar today. We have the superfetch algorithm, for instance, on Windows, but also on Linux. Whenever you request something from the disk, Linux will fetch a lot of data from the disk, way more than you requested. Working set itself is not a PRA, but it is commonly used to form process-aware PRAs. And the same approximation can then be used in combination with the other PRA techniques. And therefore, we also use the same techniques here to get the information, the reference bits. We poll the reference bits, we store the information in the global data structure, and then we make a decision. And I will now put on one slide the essentials of working set PRAs. And I will start with the page count variant, because I think it's more intuitive to understand. The working set is defined as follows. Every process has a working set size n, and every process has m mapped pages. And usually you would say that m is greater or equal to n, so there will be more pages mapped, or at least as many pages mapped as this process has as a working set size. Each page has a timestamp, and this usually is not real time because we are talking here about relative ages within the process. So you could use the process time here, or the clock that you've implemented for the clock syscall. So this value you could use here, and usually you would also, because there's no need to use real time. For the working set, then you can use the n youngest pages. That's basically the definition of what the working set is. So it has a size of n. The n youngest pages are the working set. So if someone asks you, okay, which pages are in the working set, then you can show this list of pages. These n pages are in the working set. Process-aware PRAs now swap a page that is in no working set of any process. These pages are considered swappable. A page, one of these pages will be swapped when there is a need to swap a page. And then you use a global PRA on these swappable pages. Anything, for instance, using clock, you get working set clock. Very nice. Okay, so this means that we just have to decide, is it in a working set? If not, use an algorithm that we already have. And then we can also make this adaptive, and usually you would, if you implement a working set PRA, you would make this adaptive, of course, because we started with this. So I said there should usually be the n or m should be greater or equal to n, right? You should have at least as many pages mapped as the working set size is. So that means we start probably with a value that is very small here. Maybe it's even 0 and also 0 mapped pages. And then you will update n on certain occasions. For instance, as we've seen on the previous slide, if we have memory pressure, then we can set n to n-1 for all processes. But keep in mind that every process has a separate n here. So for GTA 5, this might be at a few million or a few 100,000. And for our calculator, this might be just a few tens of pages, something like that. So for instance, when trying to swap a page, but there is no page swappable, that would be a very clear indication that you have memory pressure and you need to free something. If there are no swappable pages because they are all in the working set of some process, then n has grown too large globally. Then we decrease it for all processes. And then when we map a page, for instance, then we would increase the working set size because now the process uses one more page. Okay. Now these values will change over time, right? They will oscillate maybe. Sure. Does it pose a problem? No, because it just decides which pages or how large the working set size is and which pages are swappable. The page fault frequency for the processes, and this is something that you can actually measure in your SWAP. The page fault frequency will settle to approximately the same value for every process and will then oscillate around this value. Now, the page count variant is, if you look at resources online, you will probably not find the page count variant, but rather the time variant. So I've also put this on the slides, time variant, and I've marked in red what changes here. The working set size is now not defined by the parameter n, but by the parameter tau. All pages younger than tau, update tau, decrease tau slightly, increase tau slightly. Okay, works in the same way, just that you in one case have to perform more comparisons with is it older, is it younger, and in the other case you just work with the count and have the pages sorted somehow. Let's take a look at this illustration again, and this time we have the working set here with process 1 and process 2. And we have our accesses now also divided into accesses by process 1 and process 2. And we start with an access by process 2, and in this case I'm illustrating working set random, so it goes to a random location. So we start here, goes to a random location, maybe this one goes here, maybe this one here, here. It's random. Maybe it's turned around. And you can see here that I always add this page to this working set of the corresponding process. So you can see first there's 5. Now there's 2 added on the left side. Now we add 0 on the left side. And then we add 7 to process 1. And we can see now process 1 has the 7 in the working set and process 2 has 0 to 5 in the working set. What do we do in the next step? Well, we would access page number 6, but there is no space. So we reduce the working set size for each of these processes. And in this case, it will cut away the last page here. So this one will go back to a working set size of 0. And this one will go back to a working set size of 2. Okay. Then we perform the access that we wanted to perform. And this is an access by process 1. And now it is here, so we have working set sizes 1 and 2 now. Then we have a hit here. Okay, so now page number 7 actually is, it's still in memory. And we can see that it's now in the working set here of this process, and it's the youngest page in this working set. Access to page number 3, again, we have to reduce the working set sizes because they were again at 3 and 1, and that was too much. For pages it's full, we need to make some room for this new page here. We kick out the 2 pages here. Or we don't kick them out, but we just kick them out of the working set. Now they are eviction candidates. So we can see that C is an eviction candidate and also G is an eviction candidate. One of these 2 will be replaced now. Okay. Then in the next step, we access location number 1, and we know that this one is in no working set, right? We can't see it in any of these working sets, so it's going to be replaced. Okay. Access to number 7, we already have it here. It will be a hit. This is actually, I made a mistake here that I definitely need to fix, but you should not have this mistake in the online calculator that I provided to you on the TACOS test system website. So here I actually reduced the working set size, although it's not necessary. That's of course bad because this is a hit, right? There's no need to reduce the working set size here. And in the next step, I access this. Okay, but here in this step, it would have been necessary to reduce the working set size, so it's fine again. And the replacement then was either this location or offset number 0, so one of the middle 2 would be replaced. Okay. Then we have an access to offset number 2. It has to replace this one because this one was in no working set. Now we have the situation again that the working sets are full, but we have first an access to number 7. It's already there, and now we can see also the working set size here is 3 and 2. Still fine. We only have 4 slots in the RAM, but working set sizes, if they overlap, then it's totally fine if this grows larger. Then we have our access to offset 0. So we have to replace a page, and which page is replaced? We reduce the working set sizes as before. This means that pages 7 and 2 are still in the working sets. These 2 can be replaced. Okay. In the next step, this one will be replaced. And then access to number 4, we can again see the working sets are at 2 and 3. So we again reduce the size here. So 7, 0, and 5 will remain in there. And we can then kick out C because C is in no working set anymore. So page number 2 and load page number 4 there. And then in the last step, we will access page number 3. And page number 3, again, we have to reduce the working set sizes. And now we can replace any of these pages, maybe page number 7 this time, because it's, or not any of these pages, of course. Pages 5 and 4 have to stay in the RAM because they are in the working sets, right? But the other 2, A and H, these 2 can be replaced. And in this case, we will replace the lower one and add it to the working set, of course. Okay, so let's see whether this algorithm was fair. We got 1 hit and 7 misses in the one process, 2 hits and 6 misses in the other process. Yeah, for our small example, maybe it's fair, but you should probably try that on larger numbers. What we probably still should discuss here is the PRA design, local versus global. So the question is, where do you implement this? We had this now for the working set algorithms, that this one had some local part which decided which pages are in the working set, and the global part which globally selects which of these pages from no working set, that are no working set, which of these is going to be kicked out. So local strategies usually say, well, I only perform this replacement within one process. So I select another of my pages to replace. Then the question, of course, is the working set size fixed or is it adaptive or global from any process? You will just say, okay, I need to kick out a page and I want to decide which page is the best candidate globally across all processes, because maybe there's the calculator who doesn't need that page anymore. Working set algorithms are inherently global because they combine this information from all the processes into some global data structure that can then be used to decide which pages to evict. Global strategies are generally performing better. If the process needs more pages, then you might have thrashing, although other processes still have spare pages if you use a local strategy, right? Or if the process needs fewer pages with the local strategies again, then the memory might be wasted, although another process might be thrashing already. So global strategies perform better because local strategies have these problems. Also, maybe in looking forward to assignment 2 here, you can implement something that is called pre-swapping. Page allocation latency is crucial for performance, and if you need to swap when allocating a new page for someone, then the page fault latency will go up dramatically. Bad latency, you need to go through these steps. There's no free physical page, you just find that out. Then you find no clean pages, you need to swap out a page, wait for the disk is slow. Then you have to return the released page to the user, and this is then the step that we have been waiting for actually. So better do not let it get this far. It's not possible to entirely prevent this situation, but you can reduce how often it occurs. It's not always possible, but you can try it. And again, here we can go for these classes that we learned about from not recently used. We had this class here. This was very nice, right? Not referenced, not dirty. Was not used in a while, and it has not been modified. We can just evict it. And we already have this information, right? With all these PRAs, we have this information, so we can still just evict these pages. And then you can have a swapping thread that most of the time does nothing, but then also checks, are there unused pages that I could already write to the disk? So you swap a dirty page that has been modified to bring it into this different class, into this class that has not been referenced in a while and is unmodified on the disk. So you keep it in RAM in this during this or at this point in time. You don't kick it out, you just write it to the disk, but you set the dirty bit to 0. And now if the page replacement algorithm wants to kick something out, you can just check, oh, the dirty bit is 0, so I will prefer to kick out this page first. And then you can say pre-swap pages are evictable pages. You can just evict them. And performance-wise, this is just as good as unused pages because you don't have to swap them out. They are already swapped. Of course, the decision which pages you want to swap out or which pages you want to pre-swap, you can again make this dependent on the swapping algorithm to get also the advantages of the swapping algorithm here. Maybe also going back to Fabian's question from the chat, what if the calculator needs to do some very heavy calculations and needs some pages for that? There's also another option that you can implement, and that's page pinning. Maybe a page is required to stay in RAM. For instance, if it's some interaction with I/O memory, then you don't want to swap this page. It's not even really possible to swap this page, right? So you don't want to swap them out. If you would, something bad would happen, right? Some other process raises a page fault, the page gets reallocated, and now the I/O device does not know, the DNA transfer does not know that some other process is now using this page and will write onto that page and destroy everything. So we avoid this scenario by locking pages into memory, and they are then excluded from the PRA. So we lock the page, we pin the page into memory, and it cannot be evicted anymore. Yeah, alternatively, of course, if you have these I/O requests, you can also use kernel buffers, and kernel buffers likely are not swapped if you're not running Windows, right? Windows also swaps the kernel, but yeah, we are not implementing Windows here. And with that, we get to another round of questions and then the Q&A, and then we will also check out the exam question on this part from the TACOS website. So as soon as you're ready, I see that there are 37 there now. So I will answer just a few questions before we start with the quiz. And can I show the Q&A? Let me go back to this slide and I will show the Q&A. Why can't you just decrement by 1 instead of shifting? Would that not save space? Maybe it would, but it would be a different algorithm and probably also, it would have different aging characteristics. So you can implement that and check out whether the performance of this one is better. How many points are 100% right now? I'm not answering this question. When will Professor Peter Lipp give a lecture? Actually, I'm not sure. I will give you an answer on that. Are there any specific HDD or SSD algorithms? Adaptions in the OS itself. Yes, so there are for SSDs or HDDs, there is a different handling, especially you want to group writes together so that you don't perform too many writes, for instance, to an SSD. Also, there are certain types of operations that are more hurtful on the SSD. For instance, if you all the time update the file access times in a specific way, then this might be bad for the SSD. So the operating system might have adaptations to that. But regarding the swapping algorithms, I'm not aware of any because they perform mostly these large bulk 4 kilobyte transfers. No special shirt today. Yeah, I should have gotten out a Spectre or Meltdown shirt, I guess. How should we know if we have 10 points then? Like in any other exercise where you don't know in advance how many points you have. It's not as if you in every exercise would know exactly how many points you have at any point in time. So you have to implement things and then Is Peter Lipp your hostage? Not that I'm aware of. Okay, let's continue with the quiz. And now we have 37. Okay, I would say we can still start. So I will press the start button, check out the device, and you will get a prompt there. Which statement is wrong? Page translation is efficient because of caching. Memory layout is partially defined by the binary and partially by the operating system. A good replacement algorithm is fundamental for system performance, or working set algorithms are more fair because they are local. Which of these statements is wrong? You have to think about each of these statements now. Maybe they are somehow twisted. And most of you have already answered. There's almost the time up. And the time is up. And okay, at least some of you have listened to the last few slides. Working sets are more fair because they are actually global. They are not local, so this doesn't make any sense. They can't be more fair because they are local, because they are actually global algorithms. We just said that on like 2-3 slides ago. Page translation is more efficient is efficient because of caching. Yes, this is also true. Maybe we can do it like this. Page translation is efficient because of caching. That is a true statement. It's not a wrong statement. memory layout is partially defined by the binary and partially by the OS. Yes, we've seen that in the recap at the beginning of the lecture, and a good page replacement algorithm is fundamental for system performance. We also saw that today. If you use a bad algorithm, then you will have a lot more page faults than necessary. And with that, we get to the leaderboard, and we probably can congratulate a winner here. And that is actually a lot of you have both answers correct. And therefore I say congratulations to all of you. Very nice. And oh no, it will now list all of you here. Okay, yeah, maybe I will check out the questions in the meantime. Okay. Okay, perfect. There we are, and we go to the last slide here, which is the Q&A. So the percentage on the TACOS defines also our POC points. Yes, partially, but the tutor has some room to give fewer or more points. So in the end, it's still the tutor giving you the points. And with that, I would say we will switch to the code example. Let me just move this over here. Maybe it's better if I stay like this. And I want to open now not the slides, but I want to show you the TACOS test system like this. Yeah, and we can now go through a few examples here. Of course, we can start with another one of these if we like, just to freshen it up. Of course, we like this. Okay, let me maybe move this one a bit up so that I have some more space here. Okay, so what do we have here? We have, I will directly enter some of these things in the on the web directly. So what do we have here? We have 512 bytes page size. 512 bytes, that's 2 to the 9. So we need 5 ignored bits plus 4 bits is 9 bits for the page offset to be able to index every byte of these 512 bytes. Then the frame number, we have a 21-bit physical address, and we already have 9 bits for the offset now, so 21 minus 9 would make 12. Then the ignored bits, let's see how large this is. This is 9 plus 12 is, it's 21. 21 doesn't fit in 16, so we have to use 32, and that means we have 11 bits left over here. That means that we have, so we have one level, but we will see that in a second. Each page table entry has 4 bytes, 32 bits, and then 4 bytes. How many do fit on this one page? We have 512 divided by 4, that's 128. And how many do we need? We have 16-bit virtual addresses here, minus 9. That means we have 7 bits. 2 to the 7 is 128. So we have one level with 128 entries. It fits exactly on this page. Okay, very nice. Let's take a look at the first address here, and we will compute how this works. So let's start again with this number, and that's I need to make sure that I also see what I'm typing there. Okay, maybe like this. So page ppn. So we have 5613, and we need to split this into the page table index and the offset, because we now only have page table index and offset. And I will just, so for completeness, I will draw here maybe the struct for the pointer. So it's a 16-bit virtual address. So it's like this. This is what a pointer looks like. A 16-bit pointer. And this 16-bit pointer will consist of 9 bits offset, and it will consist of, on top of that, 7 bits PTI, the page table index. Okay, so that's the page table index and the offset. So we can basically now take a look at this address, this 5613, and we can split this up. 5613, we know that this is 8 bits. We need 1 bit from here, from the 6. So that means that this one leads to an offset. The offset will be null x 13. I will not always write this null x because all the numbers, or most of the numbers that we write are hex anyway. So we'll just write, maybe I will write null x 13. And now we need to shift this 5613 to the right by 9 bits. That's the same as shifting this to the right. I can leave the numbers here for completeness, of course, but it's the same as shifting 56 to the left, to the right by 1. This becomes 3. And the 5 actually becomes a 2, and it adds 1 bit up here to this one. So this is not a 3, but it's actually a 1011. And 1011, that's B, I would say. 2B. Okay. And that means that the PTI is, oh, we have to be careful. 2B, is that maybe too large? 7 bits. This is 4 bits. Oh yeah, this works. Okay, so the PTI can be 2B. We always have to take care that this is not too large, because it could be too large. If we get a larger pointer where the first bits are ignored or used for some other purpose, this could always be the case. The first address to look up is A00 plus 2B, and that's shifted to the left by 4. Why? 4. Let's check this again. What exactly we need to do here? We need to shift this to the left for the entry size, right? So the entry size here is 4. If the entry size would be 1, we wouldn't need to shift at all. If it's 2, we need to shift by 1. If it's 4, we need to shift by 2. Of course, because 2 to the 2 is 4. So this shifted to the left by 2. That means I can actually use a trick here. This is the same as 56 shifted to the left by 1. This is the same as A. And this is the same then as 6 becomes a C. So this is A, C. Nice. Let's check out the address AAC. Let's see whether we did a mistake so far. So I will check out where AAC is. A, and then we have here, we have to, C is at the very end of this, right? AAC. That's about here. These bits. Okay, let's copy them up. Okay. We copy them in here just so that we have them somewhere. And what we do immediately, and I will already remove, maybe I don't need to do that. So maybe I can put the numbers here. So what we have gotten from the PTE was 8801 CEF, And now what we will do is we check, is it present or not? It is present. The last bit, the valid bit, is set in this case. And we can directly read the bits here because we are already at the last level. So it's valid, it's executable, it's writable, and it's readable because that's the F. Okay. Now we get rid of these ignored bits, and we have ignored bits both at the top, 11 ignored bits. So at least these two are ignored. This one as well, we don't need it. And this one is a 0, we also don't need it. So what we have then is 1CF, and there we need to still reset the lowest 9 bits for the offset. We need to set these to 0 as well. 0, and this one is also 0, and here the next bit is already 0, so it doesn't make a difference. So this is 1C00. So this is already nice. This will be our physical page base address. And the physical PPN is this divided by page size. So we have to shift this to the right by 9. That means we have 1C shifted to the right by 1. And that becomes actually an E. Okay, let's see whether this is correct. The page PPN should be then null XE. Nice. This worked. And here the physical address would be null x1c00, but we are missing some part here, namely the offset. And the offset was null x13, so we have to add this. So it's not 1c00, but 1c13. And this means we have solved this example, and it didn't take us very long to solve this example. Okay, let's continue with questions from Menti. Of course. So in all courses until now, I actually knew if I had enough test cases points at the deadline. Yes, but in this case, you don't. You can ask your tutor if you should do more to pass, to be above the bar here. The tutor will tell you if you have to do more. Why do you have to shift to fit the size? I'm not sure what the size is referring here. I have to shift to fit the size. Where did I fit the size? Okay, could you go over this step again? Of course. So let's check out this part here with the A00. Where did this come from? This came from, if you take a look at the page again, A00, this is where the top level page table starts. This is, in this case, is our page table. You could compare this with basically value that is written in the CR3 register. On x86, this would be written in the CR3 register. That's the physical address where the top level page table starts. And now I want to access the right entry. Let's go down to address A00. And I will now do this more naively. So I will go to A00. Right, I'm here now. This is A00, and what I want to access is offset AC. Or let's start here. PTI. This is the index that I want to access. This is 2B. Let's maybe convert this. This is something that I would never recommend, but in this case I need to because I want to illustrate how this works. So B is 11. So this equals 11 plus 2 times 16, so plus 32. So this would be 43 if I'm not mistaken. But you easily introduce errors here that are not necessary. And it's actually much more complicated to do this conversion, because here I just shifted the bits a bit around and got to this A00 plus AC here. Okay. But what I do here with this shift is I want to compute how far in this page table I have to go. This page table has 512 bytes, right? one of these lines here is 16 bytes. So this 16, 32, 64, no, wait a second. So this is, yeah, 16 bytes. Yeah, exactly. 16, exactly. And it's not 500, is it 512 bytes? Let me check again. Yeah, it should be 512 bytes. So it would have 128 entries. Okay, that makes a lot of sense. 128 entries, that's what we said before. So it's 16, 32, 48, 64. Then we have 80, then we have 100 and now it gets complicated. 64, then we have 80, then we have 96. Am I off by one now? Okay, let's start this again. So you see how difficult this is. 16, 32, 48, 64, 80, 96, 112. Then we have 128. Okay, 128. This is in bytes, of course. This is not entries, right? And each entry is 4 bytes. The entire page will be 512 bytes. So this was just 128 bytes. So what do we do? This is another, so we can see that this was 64, this was 128, this is another 64, so this must be 256. So this entire page table goes over this range. Now we can see the entire page table here, all the data from the page table, all here. And we can now just go and check out which entry is which. If we have page table index 0, then we would read this value. If we have page table index 1, we read this value. If we have page table index 2, we read this value. Page table index 3, page table index 4, page table index 5, 6, 7. It will take us some time until we get to 43, right? This will take some time. Okay, so we are now at, oh no, I forgot where I am actually. I'm really bad at this. That's why I prefer to run this other approach here, where I just compute where the offset is instead of counting. Counting, you easily get that wrong. So let's start again. 0, 1, 2, 3. Okay, so then we have 4, 5, 6, 7. So, okay, so this would be 3, 7, that would be 15. The index, last index here would be 15. Then let's add another 4 lines, 1, 2, 3, 4. Then we are at offset, so this would be 31. Okay, 31, 35, 39, 40, 42, 40, 40, 41, 42, and there we are, 43. Oof, that was really complicated, but you can see how this is just an array access. You can see the entire array here, and we are accessing one element in this array, right? So far, fine. Okay, but we could also, instead of going through this array step by step, element by element, just compute the address where our element is. And we can do this by not going through this route with the 43 and counting and such, but instead skip this step and just say we can compute the address where our where this has to be. So this is where our array starts. Let me write that here. Page like this. PT starts here, right? This is where our page table starts. We just had that here, right? This. That's basically just pointing to this one here. And now we want to access actually this element. So we want to have something like an array access at null x2b. Right? That's what we just performed. We went through this and counted element by element by element by element. And what we actually want to do here is we don't want to use these array access operators because we can't do that. We are not computers. So what we do instead is we resolve this exactly as we would resolve pointer arithmetics. And we know that this one has to be multiplied by 4 because this is the data type size here. The entry size is 4. So this is A00 plus null x2b times 4. And times 4 is the same as shifting it to the left by 2. So it's A00 plus 0x2b shifted to the left by 2. And I'm running out of space here, so I will just hide the slides for a second and continue up here. So we have this one will go. Okay, we continue here. And we continue with how we compute this offset. A00 plus 2b shifted to the left by 2. This is the same as A00 plus 2b shifted to the left by 1. And this is something that I can do. Shifting to the left by 2 is complicated, but shifting to the left by 1 is easy. But we have to shift it 2 times to the left by 1. And we do this. So A00 plus, this becomes a 4. The b actually gives 1 bit to the previous one. So it's not a 4, but it becomes a 5. And from the b, we actually keep the, so the b was 1, 0, 1, 1. So we actually keep the middle 2 bits. So it becomes a 6, 0, 1, 1, 0. Okay, there are actually for single bit shifts. Think about it. How many operations are there? For every hex character, because it's just character by character, it's just one possibility. So it's only 16 possibilities that you have to look at. And then you can do this with hex numbers. 16 possibilities that you have to keep in mind. And they are sometimes as easy as shifting a 3 to the left becomes a 6, right? And this becomes, in this case, because this 1 bit is shifted up here, also b becomes a 6 if shifted to the left. But we have to shift this to the left another time, and then we also know that a, this is also something that I find quite handy, a is 10, and shifting 5 to the left by 1 makes it a 10, so it's a, and 6 to the left becomes a c. Okay. And then we have equals a, c. Does that answer your question? Let me see. Could you go over that step again? Actually, I work nicely around that. Yes. Does SWAP have a license? We have a difficult situation around the SWAP license because there are many authors that contributed to SWAP and they provided their code under different licenses. So currently, the situation that we have is that the Austrian copyright law applies, and that means that you are not allowed to share or to distribute, to build on top of SWAP, to do anything with that because it would violate current copyright legislation. You might know this all rights preserved statement. It's basically just saying that we cannot give you a license that would allow you to share the code with someone else, to redistribute it, to make modifications and redistribute the modifications. So any derived work would be a copyright violation, and it's, for us, it's not even possible at this point because we don't even have the contacts to all the authors anymore. and we can't put a proper license on SWAP therefore. Are we allowed to schedule user threads waiting for a user space lock and let themselves decide if they should yield again, or do we have to somehow tell the scheduler when they are waiting for a lock? Let me maybe remove this part, and we are also out of time. I'm seeing I will just remove this here so that we can actually see this question again. Okay, better. Schedule user threads waiting for user space lock. No, this would be busy waiting basically. Optimized with the yield. Yeah, thank you for the detailed explanation. Yeah, no problem. I'm always happy to give detailed explanations. Okay, let's see what we have down here below the memory dump. There's also something quite interesting that we still want to look at, although we are almost out of time. But let's take a look at this. So what do we have here? We have 4 algorithms, 5 algorithms even, and we should detect what type of algorithm this is, and then do something based on that. So we should somehow infer what this is. Based on the metadata, this one looks to me like it could be NFU, not frequently used with these classes. So this one, yeah, we can see write accesses and read accesses, and from which process, but it doesn't seem to take the process information into account here. The accesses page D, then this one accesses page G with the read access. Yeah, so this is dirty and referenced, and this is not dirty but referenced. Then here we have access to E. It's referenced. Okay, so it's here. B, it's a write access, so it's dirty and referenced. And then we can see here that we have another access to D, making it again dirty and referenced. And the others stay in the same state. But after some time, apparently after 4 accesses here, we reset the bits, always after 4 accesses. Interesting. So that means here B, the access to B, refreshes this page, and here again B refreshes this page, but these two now get old. Okay, so what do we have to do then? D actually was not accessed here for some time, so D is still in the memory here. G will have to replace a page. Oh yeah, actually we should be a bit more careful here. G needs to go somewhere. Where does G go? It will replace this one, because this is the cheapest to replace right now. But maybe, yeah, no, it's not correct. Let's first compute the new metadata here. So what happens? So D actually becomes a 1. This one stays a 3. This one, yeah, of course, this one will be updated with the new information here. Then we have here this access to page D. Let's see, this is B, access to page B, and this should still stay in category 3, I think. Yes. So this, in my opinion, this should be currently 0. So this should be the one that is replaced, and afterwards it's a write access, so it should be 3 then. And then we put a G here. Ah, yeah, okay, that makes sense. And that means the others stay in the same state. Okay, that was fun. Let's try this for another round. In the next step, we access offset number I. We can see that here. I can't. Yeah, this one, I. And we have a hit here, so that's great. So we keep the same data, and then we also, I need to close this one for a second. Okay, so what do we have here then? We this one stays at 1 because it's still dirty. This one stays at 3 because it's not old enough yet. This one stays at 3. This one, oh, this one could maybe now go to a different state, because B was last accessed in 6, 7, 8, 9, 6,
7, 8, 9. I think it's still in 3. It must still be in 3 because it would only go to the next category in the next step. In this step, it would be 1. Yes. We have an access to G. Would it replace something? No, because it's already there. So that means that all of this stays the same. Okay. And then we have, in this case here, this stays at 1. This one stays at 3. This one stays at 3. Next step, we access location number C. This has to replace something, so it will replace either this one or this one. So this one or this one. Which of these? The random number generator will always select the first topmost of them. Okay, so it will go here, and this is the right access, so this will now be updated to a 3. This 3, 3, 3, 3, this will become a 1. Not yet. What? Am I wrong here? Let me check. 3. Ah, yes, because here I was accessed another time here. I need to be more careful with that. I was accessed another time here, so it stays at 3. And then we have here offset G is still at 3 because it was accessed here the last time. And then we have here 1 for the last one. B was not accessed for a long time and it's still dirty, so it stays at this value. Then we have, oh, which one did we replace? We replaced the first one, I and G. Then we continue with, yeah, this is basically, we are just running through the algorithm. Let's maybe go for another algorithm because we're already a bit over time and I wanted to go through all these algorithms. The next algorithm, let's see what this looks like. This looks a bit like, you can see that with every access. So this is page E, access to E, access to E. This looks a bit like not frequently used. So this was not recently used. This looks like not frequently used. And if it's not frequently used, then this would mean that D and E cannot be replaced because they are at 2 already. And that means that A would replace either C or F. So in this case, it would replace C and F remains the same. This one has a 1 now. This is a 2, 2, and 1. And in the next step, we access F. F is already there. So it's this. And now it gets really easy for us to, okay, we have D, A, E, F, D, A, E, F, D, and now you will wonder how I know that. This is always at 1 now. D, I, E, F. So it's always, these always stay the same, and it's always, the replacement is always here. Okay, because they are accessed, but they will never be kicked out. They just count up their frequency. 2, 1, 3, 3, 2, 1, 3, 3, and 2, 1, 3, 4. Okay, so once NFU goes into such a state where only one page can be evicted, up from that point on, you only need to take care to look at whether or not it's replaced or not, whether there's a replacement or a hit in a certain step. Let's take a look at this one, and by the bits here we can directly recognize this must be aging. So we have aging, and apparently every second step it ages. Okay, and we need to decide now at this step. We don't need to check out what all of this does. We just need to look at this step, H. In step 14, H is accessed and it replaces one of these. These two have so this one and this one, these are the youngest ages, the oldest ages, sorry. So one of these will be replaced, and as we heard above, the random number generator will always pick the upper one. This one must be replaced, but it's not. Am I doing something wrong? Oh no, yeah, actually I overlooked that here's a difference. Ah, yes, they are not the same age. This one is actually older than this one. So it goes here. Yes, that makes a lot of sense. Then it's DCB. And then we have an access to F. This will be interesting. So let's take a look at this. Do we have aging? Yes, this one ages the bits. So 0, 0, 1, 1, 1, and another one. Then we are at 6. So this would be 0, 1, 1, 1, sorry, 0, 1, 0, 0, 0. 0, 0, 1, 0, 0, 0, 0, 0, and here we have a new page, so we start with this. Always for a new page, we start with a clean age with 1 and all zeros. Then we have F, and F will replace the oldest page. This is in this case this page, so we can really recognize now that this is the oldest page. So this one is replaced, C, B, and H. And here this one is not aged this time, but we have to put a new value because it's a fresh page. This one stays the same, this one stays the same, and this one also stays the same. They would be shifted in the next step. So we are at algorithm 4 now. This looks, okay, metadata. It has, yeah, this looks a bit like, it looks like working set to me because it has these two processes, 0 and 1, something like that, and collects pages there. So we have to check which page is not in a working set. F is not in a working set. We access page number A. A is already there. E is also already there. E is already there. H is also already, H is also already there. So up to this point, I don't see much of a change here. So it's H, 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 A, E, E. There's no change here because they are already all in the memory. No change. B will be the first replacement here. So this will be interesting. So we have here an access to page A in set 0. So A is here now, and A, H, E is in this set. Then we have an access to this set. So it's E, A, H, I think. Why not? Let me check. So this one stays A, and I have A, H, E. A, H, E. Oh, this is curious. I find this curious. This is wrong, I think. I did not do this correctly. This should be, I think I need to patch this in the test system because this one should be E8H. Because E is younger now and it's always added on the left side. Ah, no, it's not. Ah, sorry, I mixed this up. It's correctly implemented. The new H is the newly added page is added on the right side. You can see this here in step 8 to step 9. E is added on the right side. So always the leftmost one is kicked out. And then we have another access to E, so it goes here and here. Another access to H, so now we can show that we actually understood now how it works. A, E, H, yes, now this works. And now the access to B is of course interesting. What goes missing? Well, we started off with A and A, E, H, but we now have to reduce these working sets again. And that means we have to, of course, we don't have to kick out anything because there's only A, E, and H in the working set. F is not in the working set, so we replace F. And that means that H, A, and E can stay there. But of course, this is now not correct because B is added, so it would be A, B. And then we access page F. Now we have the problem that we have to, that I wanted to show you in the previous step already, but we only run into this problem here. The working sets are too large, and we have to kick out the oldest page in each of these working sets. So we do that, and we then see that A is to be replaced. It's not in a working set anymore, so we add it to the working set of process 0. Okay, B, oh, not A, F. We access F here. B, F, and then H, E, and B stay the same. Okay, and then in the last algorithm we have an access to E. And what do we have here? This is Pseudo-LRU. This stores when it was last accessed. Okay, so this was, okay, then we replaced the one that was least recently used. So this one is replaced. So it's actually in replacement because E is not in the memory already. E is placed here, B, A, D, and this is 11, 14, 12, and 13. And here we have an access to D. This is fine. We don't need to replace anything in this step. And that means we have here 11, 14, 12, and then 15. And with that, we are through the examples on this page. And if you want to compute through these examples, you can also do that. And you will be able to share a link. There's link to this instance here. And if you share this with us, and if you have any questions on the specific instance that you are working with, then we can answer your questions on this specific instance that you are working with, if anything is not working as you would expect it to work. Are there any questions? Let me check in the Q&A. I don't see any questions in the Q&A. I only see a thumbs down. Someone didn't like my explanations. Fine. We can also not explain things. Also happy with that. Okay. Let's see. No questions. I think this was a bit, I rushed a bit through this. I know, but we are already out of time and I didn't want to spend too much time on this part now. But we can also, in the next lecture, we can also, maybe we can introduce an extra lecture where we just focus on exam questions, if you like, and go through exam questions. Yeah, probably before the test, that would make a lot of sense. Yeah, if there are no questions, I don't see any questions in YouTube. I don't see any questions in Menti. Then I would like to thank you for your attention. And then we see each other next week in the lecture. And we will talk about scheduling and file systems there. See you there. Bye.